What about the potential energy of point particles? We just talked about the potential energy of a particle located in a constant electric field. Now, what about if the particle is located in a region of space that has an electric field produced by another particle? So you have your charge Q, and you bring another one. Let's say that you have another charge, little q here, at location 1, and you let that particle move. Let's say that is positive. And you let that particle move due to the electric force between location 1 and location 2. Let's say that that particle moved that way. So you start with some initial distance from the Q particle R1, and you end up with this distance at location 2. So the question is, what's the work done by the electric force when the particle moves from 1 to 2? So the work done by any force, of course, is the integral of the force multiplied by the distance, by the displacement, and you're going from 1 to 2. The force is Q divided by the distance squared, and you're integrating this over, we're moving along a line, a radius, so that's dr, and you're going from R1 to R2. Right? So the constants you can pull out of the integral, and you have the integral of dr over r squared, which is a pretty easy integral to do, right? So the answer is that the work done by the electric force goes like -1 over r, and you're evaluating this between R1 and R2, which means you just replace R2, replace in your equation for R2, and you subtract the equation evaluated at R1. So Q, and this is -1 over R2, minus with minus plus 1 over R1. Okay? So the electric force is a conservative force, which means that the work done by the electric force should be equal to the change in the potential, to the negative of the change in the potential energy of the particle. Okay? So that means that the work done by this electric force, when it goes from 1 to 2, should be equal to the electric potential energy location. The final is 2. I'm going to do it slowly here. 2 minus 1. So that will be the electric potential energy at point 1 minus the electric potential energy at point 2. So if you compare the two expressions, you get Q over R1 minus Q over R2 should be equal to the electric potential energy of the particle at location 1 minus the electric potential energy of the particle at location 2. So what that equation is suggesting, not just suggesting, telling you clearly, is that the electric potential energy of point charges can be described by the equation Q between two charges, Q and little q, can be described by this equation. There is in principle a constant, some u sub 0, because when you, all this is telling you is the difference between the difference between the function evaluated at R1 and the function evaluated at R2. So if the function had some constant that does not depend on r, that constant of course would be cancelled. It would cancel with each other, so you would just get the same answer. So in principle you could have a constant value for the added to the function potential energy. Since that's kind of arbitrary, we can choose it to be 0, because we can say, it's just a convention, we can say that the electric potential energy of the two particles, when the particles are infinitely away from each other, should be 0. There's no reason to add some number, arbitrary number, and say that even though the particles are infinitely apart, there is some energy stored in that system. That doesn't make a lot of sense, and it just complicates your life. So the standard is to say that the potential energy when r is equal to infinity is equal to 0, which immediately tells you that the best way to choose U0 is to say that it's equal to 0. This arbitrary constant there. So the final answer then is that the electric potential energy between 2 point charges is this. Right? And this applies to 2 point charges. So it clearly depends on the distance between the charges. The further away they are, the less potential energy you can assign to that pair of charges. The closer, the stronger the potential energy. Imagine two positively charged particles and you push them really close together. You're basically increasing the potential energy of that pair by a lot because R is small. And if you let go, then that energy that you have accumulated in that system is going to be given to the charges in terms of kinetic energy. So they will push each other away. And as they're pushing each other, they're going to gain kinetic energy, right? So now that you have an expression for the potential energy between two point particles, you can use that to solve problems where, for example, you have the collision between two charged particles, right? In the collision between two charged particles, there is two quantities that will be conserved. One will be the momentum. Every time you have a collision, no matter what kind of collision you have conservation of momentum. And the other quantity that will be conserved is energy. Right? The particles will never touch each other. If you're talking about particles that are just fundamental particles or that are not squishy or something like that, the particles would bounce off each other. Suppose they're both positively charged. So the energy of that collision will be conserved. So there's two equations that you can use to describe and to find out information about a collision between two charged particles. You can use the potential energy equation that we just derived here and put it in a conservation of energy equation, and the other conservation law that you can use is momentum. Right? So conservation of momentum, conservation of energy would solve the problem for you if you're dealing with a collision between charged particles. Notice that the potential energy will be positive if the two charges have the same sign. But if the two charges have different signs, one plus, the other one negative, the product of the two charges is negative, and therefore, because it shows up in the equation for the electric potential energy will also be negative. Okay, so a system composed of two particles with different signs has always negative potential energy. Okay? Only when they're infinitely apart, they will have zero potential energy. But at any other distance that is not infinite, one positively charged particle, one negatively charged particle, they have negative potential energy. Okay? And if they're both with the same sign, both positive, both negative, then they have positive potential energy. If you have a charge Q here, and you take your little Q from infinity, and you bring it all the way here, where now you are at a distance r from big Q. What is the work that you have to do? You have to apply, of course, let's say that for simplicity both are positive, so you will have to apply force to this thing, to this system. Otherwise they're not going to do that. The little particle is not going to get close to the other one since they have the same sign. So I need to apply an external force to bring those particles closer together. Just like bringing two magnets that have the same polarity, you have to push to get them close. So what's the work done by that external force? I don't have to integrate. I already did an integration and that's enough, right? The work done by the external force is equal to what? According to the conservation of energy equation, tells me that when an external force does work on a system, what happens to the energy of the system? The energy of the system increases, right? Or decreases depending on the sign of the work. But clearly I'm going to be doing some positive work here. I'm pushing it to the left and the particle is moving to the left. So this is going to be positive. So that means that the energy of the system it's going to go up. If I move that particle from infinity to the location r, and I do that slowly, I'm pushing, but I'm not making it accelerate. It's just moving slowly, little by little, right? When it finally arrives at location r, the particle has a final energy, right, which will be given by the electric potential energy between the two particles, right? The final energy of the particle this is the final, this is the initial at infinity, right? The final energy of that particle is the final kinetic plus the final electric potential, right? And you're subtracting the initial energy of the particle, which is the initial kinetic plus the initial electric. Since I said that the particle is going to move very slowly, I'm not going to let this particle accelerate and gain kinetic energy. I'm starting from 0 kinetic energy, and I'm going to end up with 0 kinetic energy. Okay, that just depends on how I apply the external force. I can do that. Definitely, I can do that. If I'm starting infinitely far away, the initial potential energy of the particle is also 0, as we defined it previously. So that means that the work done by that external force is simply equal to the potential, electric potential energy at the location where you leave the particle. And we know how much that potential energy is, right? It's K, Q, Q divided by whatever distance I leave the little q particle away from the big Q. So another way to look at the potential energy is that it's exactly equal to the work that an external force would have to do to get that system of two particles to be close to each other, right? If the two charges are negative, does this equation make sense? No, sorry, if one is positive and the other one's negative, what is this equation telling me about the work done by the external force? It says that the work done by the external force is negative. Does that make sense? So if this was positive and the little q was negative, what would the external force have to do to make sure that the particle moves very slowly from infinity and it ends, or you leave it at the location r with also 0 velocity? The external force has to be holding on to the particle, right? Because the particle, the little q particle, would be pulled towards the big Q particle. And if you let it alone, it would accelerate, right? But you don't want that acceleration to happen. You're holding it, you're just letting it go slowly, little by little, until it has reached the location R. So in what direction should the external force be pointing to do that job? It should be pointing to the right, as opposed to the left in this example, right? And the displacement will be to the left, and the external force is pointing to the right. So the force, the work done by the external force will be negative. Force and displacement are pointing in opposite directions. So yes, when the charges have opposite signs, the work done by an external force would also be, to bring the particles at the location R, will be negative, just like the equation is suggesting.